Okay. So today I'm going to begin 1.5, which is called Elementary Matrices and a Method for Finding A Inverse. In this section, we will develop an algorithm for finding the inverse of a matrix. So far, we only know a formula for a 2 by 2 matrix. So if A is A, B, C, D, if it's 2 by 2, then we have a formula. We know that if the determinant of A, which is defined to be AD minus BC, if that is not zero, then A inverse exists, and we have a formula for that. 1 over the determinant of A, and here you have D A minus B minus C. So what if you have a 3 by 3 matrix? What if you have a 4 by 4 matrix that is invertible? How would you find the inverse of that? So this is something that we're going to learn in this section. We're going to learn two different methods of doing that. One is called the adjoint formula. The other one is called the inverse algorithm. Today, we're going to learn about the algorithm, the inversion algorithm. The other method we will learn later on after having studied determinant. So in section 1.1, we learned about elementary row operations. If you remember, there were three types of row operations. You can swap two rows. You can multiply a row through by a non-zero number, and you can add a multiple of one row to another row. These are the three row operations. These row operations, all of them are reversible. That is, you can cancel the row operation. And here are the three row operations listed, 1, 2, 3, and here are the canceling operations. So if you interchange two rows, how can you cancel what you just did? You just need to have to interchange the same two rows. So for example, if you swap row 1 and row 2, how can you cancel this operation? By performing the same operation again. So you can swap the same two rows, and this will cancel the row operation you just did. The other row operation is multiplying a row through by a non-zero number C. How can you cancel that? You would multiply the same row by 1 over C. And 1 over C would exist because C is not 0. And if you're adding a multiple of row I to row J, you can cancel this operation by adding negative M times row I to row J. So for example, you add 2 times row 1 to row 2. How can you cancel that? You add negative 2 times row 1 to row 2. That would cancel what you just did. Notice that these canceling row operations, so the three canceling row operations that I describe here, are actually elementary row operations themselves. So swapping two rows, that's an elementary row operation. Multiplying a row by a non-zero number is an elementary row operation. And adding any multiple of one row to another row is a row operation. So note that the reverse operations are also elementary row operations. And since every row operation is cancelable, then you can always recover a matrix that you have done a series of row operations on by doing the reverse operations. So if B is obtained from A by performing a sequence of row operations, it is possible to perform a sequence of canceling row operations to recover A from B. So imagine you perform a row operation, you go from A to B, you perform another row operation, you go from B to C, you perform another row operation, and let's say eventually you arrive at a certain form. Let's say you arrive at the row echelon form. It's not writing. A, B, C. Okay, so you perform a series of row operations, and from matrix A, you go to matrix R, which is, let's say, in the row echelon form or reduced row echelon form. Then what I'm saying here is that you can perform canceling row operations and go back and recover A from R. Any questions so far? Now, definition: two matrices A and B are said to be row equivalent if either one can be obtained from the other by a sequence of row operations. So if you have a series of matrices like this, so A, you perform a row operation, you get B, you perform a row operation, you get C, you perform a row operation, you get D, and all the way, let's say, until you are at the reduced row echelon form, or any form. Then all of these matrices would be row equivalent with each other, because each one can be obtained from the other one by performing a sequence of row operations. Is that clear? The definition of row equivalence. So if you have a matrix A and a matrix B, so that one of them can be obtained from the other one by performing a sequence of row operations, then you have two matrices that are row equivalent. Okay, next. Next, we're going to define a certain type of matrix, which is called an elementary matrix. Elementary matrices are always square matrices, 2 by 2, 3 by 3, 4 by 4. And this is the definition. An elementary matrix is a square matrix that is obtained from identity matrix by performing a single row operation. So you have to begin with the identity matrix, which could be I2 or I3, and perform a single row operation on that identity matrix, and you have an elementary matrix. So for example, if I multiply the second row of this identity matrix by -3, I get this matrix, which is an elementary matrix. Or if I swap row 1 and row 2 of I3, I get this matrix here, which is an elementary matrix. Or if I have I3 and I add 3 times the third row to the first row, so row 1 plus 3, row 3, then I get this matrix, which is an elementary matrix. So an elementary matrix is a square matrix that is obtained from identity by performing a single row operation. So it's important that it has to be just one row operation. If you have to do a couple or 3 row operations, it's not an elementary matrix anymore. Yes, so you should be able to get E from I by doing a single row operation. That makes E an elementary matrix. So is it clear, the definition of an elementary matrix? So I'm going to give you another example. This 4 by 4 matrix is I4. That's identity matrix from the realm of 4 by 4 matrices. Yes. Now, if I perform, let's say, -2 R2, that's a single row operation. Yes. Then I get this matrix here: 1, 0, 0, 0, 0, -2, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. This matrix here is an elementary matrix because I got that from I by performing a single row operation. Okay. Now, there is a very interesting relationship between matrix multiplication and performing row operations. So this is the theorem here. So this theorem establishes a very interesting relationship between matrix multiplication and performing row operations. So the theorem says, if E is an elementary matrix, then multiplying matrix A on the left by E, that is performing EA, multiplying matrix A by the elementary matrix E on the left, applies the corresponding elementary row operation on A. So by multiplying E and A in this order, I'm actually applying a row operation on A. Which row operation? The corresponding row operation that was used to obtain E from identity. So is it clear, the theorem?
Could you repeat that, please?
Yes. The theorem establishes the relationship between performing a row operation, that is doing any of those three row operations, and matrix multiplication. So what does the theorem say? It says that if you have an elementary matrix E, and then you multiply A by E from the left, that is, you perform this. You multiply A by E on the left. Then it's as if you are performing the corresponding row operation on A. For example, I think these examples can clarify the situation. So you remember these three matrices over here? Yes, so E1, E2, and E3. Each one of these matrices, they correspond to a certain row operation. Yes, so this elementary matrix E1 actually represents this row operation. E2 represents this row operation. E3 represents this row operation because you need to perform this row operation on identity to get E3. Okay, so now what would happen if I multiply this matrix A by E1? So let me just read E1 again. E1 is over here, 1, 0, 0, minus 3, and E1 is corresponding to this row operation. E1 corresponds to multiplying the second row of I2 by -3. Okay. Now, what happens if I multiply the matrix A and E1? So I put E1, 1, 0, 0, minus 3 on the left, and A, 2, 3, 1, -1, 5, 2 on the right. The theorem says that if you multiply these two matrices, if you perform this matrix multiplication, it's as if you are performing this operation on this matrix. So you should get 2, 3, 1, because the first row does not change, and the second row gets multiplied by -3. So you should get 3, -15, and -6. And you can try this. I'm going to give you 1 minute. Do the multiplication. So forget about elementary row operations, forget about elementary matrices, multiply these two matrices and see what happens.
Sir?
Yes.
If I understood correctly, the reason why it's as if you add that as you wrote before, -3 R2, it's because when you multiply an identity matrix by and for example A, it gives the exact same initial matrix. So if you multiply by elementary matrix, it's as if you're applying that row operation on the initial matrix, correct? Does that make sense?
So you're explaining why this happens?
Yeah.
Yeah, the why, I'm not sure if I understood your explanation correctly. I think the proof is in the book for this one, and I'm not gonna prove it. But let me just check. I'm not even sure that the proof is in the book. Let me just pull out the book. Look at section 1.5. No, the proof is not there in the book. And to be honest, I don't think this is something that I can just explain. Definitely, for sure, it can be proven rigorously on paper. But the reason for that is not very obvious to explain. What is really important for me is to just, and for you to understand the theorem. This elementary matrix, yes, it corresponds to a certain row operation, because this row operation was the one that was performed on identity to obtain this matrix. And the theorem says, now if you multiply a matrix by this elementary matrix on the left, it's as if you're performing this row operation. So that's what the theorem says. So did you multiply? Did you check this out? Of course, this is not a proof, but just an example. But it shows how this theorem works. Let's do another one. So E2 is obtained from the identity matrix by swapping the first two rows. So that means if I multiply a matrix by E2 on the left, this operation, this matrix multiplication, will have the same effect as this row operation. So here we have an example, matrix B, which is 3 by 2. So I want you to multiply E2, which is 0, 1, 0, 1, 0, 0, 0, 0, 1. Yes, I want you to do this. Multiply E2 and B and see what happens. This is B. So 0, 1, 0, 1, 0, 0, 0, 0, 1. And B is given to be 0, 2, 5, 1, 7, 5. Do this next multiplication and see what happens.
Sir?
Yes?
Can we multiply like on the right?
No, no,
Okay.
no. It has to be on the left.
Okay, so that's why they're specifying on the left.
Exactly. So it
Okay.
says if E is an elementary matrix, then multiplying matrix A on the left by E applies the corresponding elementary row operation on A. So since this one is corresponding to this row operation, yes, then by multiplying matrix B by E2 on the left, you are performing this row operation on B. So what I expect is this. Yeah. Just
Okay,
swapping
and I have another question.
Yes.
What's like the use of it? Like, do we use it in calculations or
Yeah.
just to simplify it?
We're gonna use that. All the things that I'm trying to build up these arguments so that you understand the inversion algorithm.
Okay.
Because we're gonna use these elementary matrices in some algebra in order to prove the inversion algorithm. And then matrix C is a 3 by 3 matrix. And if I multiply C by E3, that would be the same as performing the corresponding row operation on C. So if you go back and look at what E3 is obtained from I by performing this row operation. That is adding 3 times the row 3 to row 1. So if I multiply this particular matrix by E3 on the left, it's as if I am adding 3 times row 3 to row 1. So if you actually do the multiplication, you're going to get 3 times. The second row will not change, the last row will not change, but the first row will change. So 3 times this is going to be -3 added to this -1. 3 times this is 6 added to this 7. 3 times this is -3 added to this 2. And you can also perform the operation using the definition of matrix multiplication, and you can verify this.
Sir,
Yes?
would you just mind scrolling up to the elementary matrix rules again, please?
For the definition?
No, just those. Thanks.
Sure. You guys, you know, you have this document on layer, yes?
Yes.
Yeah. Okay. So the next theorem is every elementary matrix is invertible. So these elementary matrices that we were talking about, a matrix that is obtained from identity by doing a single row operation, all of them are invertible. And the inverse of these elementary matrices, those inverses are also elementary matrices. So that's the theorem. It has a very easy proof. Let's assume E is obtained from I by performing a certain row operation. So imagine that there is a certain row operation, and you perform that row operation on I, yes, and then you get E. Then E prime that is obtained from I by performing the canceling row operation would be the inverse of E, because so you have I, yes, and you perform a certain row operation on I, and you get E. So E is actually the same as having EI. Now, if you perform the canceling row operation on this, which is the same as multiplying this matrix by E prime on the left, it's as if you cancel what you did. So you perform a certain row operation on E, and then you cancel that. What do you get? You get I back. That makes E prime E equal I. That makes these two the inverses of each other. So actually E prime is the inverse of E. So I'm going to just read the proof again. Let's assume that E is obtained from I by performing a certain row operation. So up there, we established that for any operation, there is a canceling row operation. For any row operation, there is a canceling row operation. And the canceling row operation is also an elementary row operation. So that means there exists a canceling row operation for the row operation that created E. Now, let's use that canceling row operation and create a new elementary matrix, E prime. Then E prime that is obtained from I by performing the canceling row operation would be the inverse of E, because if I multiply E by E prime on the left, or if I multiply E prime by E on the left, it's as if I am performing the canceling row operation. So I began with I performed a row operation on I got E. Now I do the canceling row operation. What do I get? I get I back. That makes E and E prime the inverses of each other. And since canceling row operations are themselves row operations, then E prime is also an elementary matrix. Very good. And it's also very easy to find the inverse of an elementary matrix. For example, if I have this elementary matrix, let's say 3, 0, 0, 1. So you agree that this is an elementary matrix because I obtained this from I by doing this row operation, 3 times row 1. Yes. So just imagine you have I2, which is 1, 0, 0, 1. If I perform this row operation, I'm going to get this elementary matrix. Now, what is the canceling row operation for this? The canceling row operation would be 1 over 3 row 1. So if I perform this canceling row operation again on the identity matrix, I'm going to get 1 over 3, 0, 0, 1. This is like having E, and this one would be E inverse. And you can check that. You can multiply them. You can see that if you multiply E inverse or E inverse E in any order, you're going to get the identity back. So in order to find the inverse of an elementary matrix, you only need to think about the canceling row operation. And then you perform that canceling row operation again on identity. That will give you the inverse. So in example 3, it says find the inverse of matrices E1, E2, and E3 from example 1. So let's do that. So E1 is corresponding to this row operation, 3, row 2. The canceling row operation to -3, row 2 would be -1 over 3, row 2. So I'm going to perform this row operation on I, and that will give me the inverse of E1. So E1 inverse would simply be 1, 0, 0, -1 over 3. And again, you can do this. You can just try multiplying E and E inverse that we just found in this order or in the other order, and you will see you'll get I. Make sense? Let's find the inverse of E2. When I look at E2, I realize that E2 is corresponding to this row operation, swapping row 1 and row 2. And I also realize that the canceling row operation for this is going to be exact same row operation. I have to perform the exact same row operation, that is swapping the same 2 rows, in order to cancel what I just did. So the inverse of E2 is going to be exactly E2. So 0, 1, 0, 1, 0, 0, 0, 0, 1. So if I perform the same row operation again on identity, I'm going to get exact same matrix. And you can try this. If you multiply E2 by itself, you're going to get I. And the reason is that it's like this. You have I, you multiply by E2, that is as if you're swapping the first 2 rows of I. And then you multiply the result by E2 again. That means you're swapping the same 2 rows again. So swap, swap, you have canceled, you've done nothing. So you get I. And for the last one, when I look at E3, I realize that this is corresponding to this row operation, adding 3 times row 3 to row 1. Then what would be the canceling row operation? Canceling row operation would be row 1 minus 3 row 3. That is adding -3 times row 3 to row 1. So I begin with I3. I perform this canceling row operation on I3. I'm going to get 3, no, I'm going to get negative 3 times this to this, 1, 0, negative 3, 0, 1, 0, 0, 0, 1. Yes? So this would be E3 inverse. And again, you can check this. If you multiply E and E3 in any order, you'll get the identity matrix I3 back. Okay. So far, we know how to find the inverse of any elementary matrix, yes? So it could be 3 by 3, 4 by 4, whatever. That elementary matrix is obtained from I by a row operation. You just think about the canceling row operation, whatever that canceling row operation is, you're going to perform that canceling row operation on identity, and you will find the inverse of that elementary matrix, which itself is going to be an elementary matrix. Are we good? Okay, so now we have a theorem, which is probably the most important theorem in linear algebra. It's called the theorem of equivalent statements. So this theorem begins with 4 statements that are all equivalent, meaning one of them implies the other one. That is, if one statement is true, then the other one is true, and if one statement is false, the other one is also false. So these 3 are either all of them are false or all of them are true for a certain matrix. That's the meaning of equivalent statements. And then as we go on in the semester, we're going to add some more statements to these 4 statements. So this is called the equivalent statements theorem. It says if A is an n by n matrix, then the following statements are all true or they're all false. So what are the statements? A is invertible, or in other words, A inverse exists. A is invertible or A inverse exists. That's the same thing. A statement B says the homogeneous linear system AX equals 0 has the trivial solution only. Has the trivial solution only. That means this system will have a unique solution, and that unique solution would be the trivial solution. And the trivial solution means X could only be 0, the origin. Part C of the theorem says that the reduced row echelon form of A is I. That is, you can perform a series of row operations on A, and eventually you will arrive at identity. So that's part C. The reduced row echelon form of A is I. And finally, A can be expressed as a product of elementary matrices. So there is a way of writing A as a product of elementary matrices. Now, these statements are equivalent means if you have one of them as true, then the others are also definitely true. And if one of them is false, then the other ones are also false. So in order to prove this, we can do this. We can show that A implies B, and then B implies C, and C implies D, and D implies A. That would make them all equivalent, because then A implies C, and C implies A, and D implies, and C implies D, and D also implies C. That would make all of them equivalent statements. Are we good? Do you understand the theorem? So I think in some chapters of the book, towards the end of the book, we're not going to cover all the sections, but there are some sections in the book where this equivalent statements is recited, and then it has 12 statements. So as I said, this is the most important theorem in linear algebra, and then as you learn more statements are going to be added to that. I think we're going to go up to 7. I'm not sure. We'll see. But anyway, we begin with these 4 statements that are equivalent. A is invertible. That is equivalent to this homogeneous linear system has the trivial solution only. It is equivalent to the reduced row echelon form of A is I. That means you can perform a series of row operations to transform A to the identity matrix. And the 4th statement says that A can be expressed as a product of elementary matrices. Now, and this is the way that we prove that. We prove A implies B, B implies C, C implies D, and D implies A. Okay, let's look at the proof. So from A to B, we want to prove that if A inverse exists, then this system has the trivial solution only. It's very easy because if A inverse exists, so now A inverse, we take that to be the assumption. So let's say A inverse exists. Then this linear system can be multiplied by this A inverse, which is not imaginary and exists, on the left. So we can multiply A inverse AX and A inverse times 0. So we multiply this system by A inverse on the left, and then since A inverse A is I, we get IX is equal, and we also know that any matrix times 0 is 0. That means X is 0. So if A inverse exists, then this system can only have one solution, the trivial solution. So that establishes A implies B. Now, how does B imply C? So at this point, we're going to assume that AX equals 0 has the trivial solution only. And we want to prove that if this is the case, then A can be reduced to I. So for that, we need to think about the Gauss-Jordan elimination. So imagine you're given this system and you want to solve this system by Gauss-Jordan elimination. So you would create an augmented matrix, and the augmented matrix is going to be like this. You put A here and you put 0 here. And then you would perform a series of row operations on this matrix so that you can transform that to the reduced row echelon form. And then from the reduced row echelon form, you can find the solution. You can actually see whether it has unique solution, it has infinitely many solution, no solution. Yes. So this system definitely does not give you any contradiction, because the reduced row echelon form is going to have a column of 0 here. Notice that none of the row operations will change the column of zeros at the end, because you can multiply a number by any non-zero number, it will still be 0. You can swap rows, and since all of them are zeros here, that column would not change. You can add a multiple of 0 to 0. That would also not change this column. Yes. But if this system has the trivial solution only, that means it has unique solution. If it has unique solution, that means you have the same number of leading ones as variables. And since you cannot have more than one leading one per row and more than one leading one per column, here you must have I. Make sense? That means A can be transformed to I. You need the same number of leading ones as unknowns, because you want the system to have trivial solution only. This is given. The only way you can have the same number of leading ones as variables is that if you have exactly n leading ones. And if you have n leading ones, since you cannot have more than one leading one per row and more than one leading one per column, then this has to be I. From C to D. So we want to, if the reduced row echelon form of A is I, yes, how can we write A as a product of elementary matrices? So here we're assuming that we have C, we want to prove D. So what do we assume? We assume that A can be reduced to I. This is the assumption. What are we trying to prove? We are trying to prove part D, which says A is expressible as a product of elementary matrices. Okay? So what does this mean? This means I can start with A. I can perform a series of row operations on that. Notice that when I multiply a matrix by an elementary matrix on the left, it's as if I am performing a row operation on that. So E1A is like performing one row operation on A. E2 times E1 times A, that would be performing a row operation on the result. So I can perform a series of row operations, first E1, then E2, all the way to EK, and eventually I'll get I. Make sense? That means this part here is actually A inverse. How do I know? Because this matrix that I put inside brackets times A is actually I. If I can find a matrix and multiply that matrix by A and I get I, by definition, that matrix is A inverse. So we have this. Now, if I invert both sides, I'm going to get A inverse inverse is EK E2 E1 inverse. But A inverse inverse is A. And this one is going to be E1 inverse times E2 inverse all the way to EK inverse. So that, and we also established that each elementary matrix is invertible, and the inverse of that elementary matrix is an elementary matrix. So this is an elementary matrix. This one is also an elementary matrix. The last one is also an elementary matrix. So I was able to write A as a product of elementary matrices. So that way, from C, I get D. And finally, how do I get from D to A to complete the circle? If A is a product of elementary matrices, since each elementary matrix is invertible, then A has to be invertible. Because we had this theorem before that if you have a bunch of invertible matrices, for example, you have A, B, C, and all of them are invertible, then the product is also invertible, and the inverse is going to be C inverse times B inverse times A inverse. We learned that in 1.4. So here, this is the assumption. A is a product of elementary matrices. Okay, then since each elementary matrix is invertible, the product must also be invertible. So that shows that D implies A. So if A is a product of invertible matrices, then it has to be invertible. That closes the circle and makes all the statements equivalent. I understand if you feel confused a little bit, but hopefully, or maybe not. Maybe it's very clear for you. I really don't know. But you can just go back to the recording later on, stop it, think about it. You can read the book and think about it. It's a very coherent and I find it very interesting theorem. Okay, so I probably will not ask you to prove this theorem, especially not in the test, because the tests are going to be online. And even the final exam, I probably will not ask you to prove this theorem, but what I expect you to know is the theorem itself. So you need to know these, you need to memorize them. Memorize the four, it's very important, the four equivalent statements. That A is invertible, it has the same meaning as this homogeneous linear system has the trivial solution only. It is the same as A can be reduced to I. It is the same as A is expressible as a product of elementary matrices. So if you don't know how to prove it, that's okay, but you're expected to know the theorem. Are we good? Now, the spin-off from this theorem is that method I was talking about, the method of inverting elementary matrices. Actually, when we said that, if you look at part A and part C, part A is A invertible, part C is the reduced row echelon form of A is I. That is, you can begin with A, you can perform a certain row operation, you get a matrix, then you can perform another row operation, you get another matrix, and then you can keep performing row operations, and eventually you get I. Yes, that actually gives us A inverse, because that means that A inverse is actually EK, E2, E1. So this matrix that is inside brackets is actually A inverse. That gives us a method of finding A inverse. So a method for inverting elementary matrices. Yeah, it's not a method for inverting elementary matrices. It's a method of finding the inverse of an invertible matrix. We just saw that assuming A is invertible, then we have this. Okay, but we can multiply both sides by A inverse, and if you multiply both sides by A inverse, we get this. So A inverse is simply EK all the way to E2, E1. So if I multiply this side by I can do that, right? Because I is like having a 1. Then it tells me that whatever sequence of elementary row operations that I am performing on A to get I, if I perform the same sequence of row operations on I, I'm going to get A inverse. That's what this tells me. Is that clear?
I don't think I quite understood. Would you mind me explaining, please?
Yes. So we said that if A is invertible, then there exists a sequence of row operations. So you can do a finite number of row operations, for example, K row operations. And by performing these row operations on A, you will get I. Make sense? And when I multiply A by E1 on the left, what am I doing? I'm performing a row operation, right? Then I multiply this result by E2 on the left. I'm performing my second row operation. And I can keep doing that. I can keep performing row operations, K row operations. Eventually, I'll get I. That's what the theorem says. If A is invertible, I can do this. We're good so far?
Yeah.
Now, if I just put these inside brackets, isn't that A inverse?
Yeah.
Because that matrix times A is I. So A inverse is basically this. Yes. Now, am I just allowed to put I here? Because I is like a 1. I can multiply a matrix by I on either side. It doesn't change it. So what does this mean? This means there is a sequence of row operations that I can perform on A, I would get I. If I perform the same row operations in the same order on I, I'm going to get A inverse. Is it clear now?
Yes, thank you.
Okay, so let's do that. This equation means that the same sequence of row operations that reduce A to I will transform I to A inverse. So we're going to use this method to find the inverse of this matrix here. We have the matrix 1, 2, 3, 2, 5, 3, 1, 0, 8. So what we do is we're going to put I next to it. Yes. And then, so this is A that's given, and we're trying to find A inverse. So that's the first step we take. We put A here and we put I next to it. So it's like this. We put A and then we put a dashed line and then I, like that. Then we begin performing row operations on A. We just follow the Gaussian elimination or Gauss-Jordan algorithm. We perform row operations on A, and whatever operation we perform on A, we perform the same row operation on I. And we keep doing that until at a certain point on the left, we're going to get the identity. I, a 1. At that point, on the right, we will have A inverse. So that's the method. Because as I just explained, the same row operations that you perform on A to get I, if you do the same row operations on I, you're going to get A inverse. Make sense? So your first step, you put A here and I here, the identity matrix. And then you begin the row operations as usual. I need to get a 0 here and a 0 here. So row 2 minus 2, row 1, row 3 minus row 1. And then you perform these row operations on the whole matrix, including this part. So negative 2 times this to this gives you 0. Negative 2 times this to 5 gives you 1. Negative 2 times this, negative 6 added to this gives you negative 3. And negative 2 times 1 added to 0 gives you negative 2 here. And negative 1 times this to this 0, negative 1 times this to this negative 2, negative 1 times this to this 5, and negative 1 times the 1 here added to 0, negative 1. So that's what I mean. You perform the operation as if you have only one matrix. Next, I already have a leading 1 here. I need to get a 0 here. Yes. And for that, I would have to do row 3 plus 2 row 2. So I perform that row operation. I'm going to get a 0 here. And when I do 2 times this added to this, I'm going to get a negative 5 here. 2 times this added to this, I get a 2 here. And 2 times 0 added to 1, no change. Next, I'm going to get zeros above. I'm going to get a leading 1 here. So for that, I would need negative 3 row 3. So I multiply the last row by negative 1. So I get 5, 2, and -1. Next, I need to introduce zeros above this leading one. So 3 times this added to this, -3 times this added to this. I perform this operation on the whole matrix. And the last step is to get a 0 here. So I need to do row 1 minus 2, row 2. And I also do that. Eventually, I get I. And the moment I get I on the left, I have A inverse on the right. So A inverse is this matrix here. Make sense? So what happens if I cannot get I? If I cannot get I, it simply means that A is not invertible. Because if A was invertible, I would be able to get I. That's what the theorem guarantees. It says that if A is invertible, A is reducible to I. So if at some point when you're doing these row operations, you have a row of zeros, the moment you get a row of zeros, you have to stop because you know that, okay, this cannot be reduced to I. That means A is not invertible. So here we have an example. We're trying to find the inverse of this matrix B. And this is going to happen. The appearance of a row of zeros on the left side is an indication that the matrix is not invertible. So let's try this. So I give you this matrix B here. So this matrix. And I ask you to find the inverse of that matrix. So what do? You're going to create a bigger matrix like this. You put B here, -1, 2, 5, dashed line, and you put I3 here. You put I3 because this is a 3 by 3 matrix. And you begin doing row operations in order to transform the left side into I. That's your goal. So if you succeed, then on the right, you're going to have the inverse of the original matrix. If you don't succeed, if at some point you hit a row of zeros, then you know that you can stop there and you just say A is not invertible. So let's see. I need to do row 2 minus 2 row 1 and row 3 plus row 1 to get zeros here. So 1, 6, 4, 1, 0, 0, no change in the first row. -2 times this to this, 0. -2 times this, -12, added to this, -8. -2 times this, -8, added to this, -9. -2 times this, added to this, -2, 1, 0. This added to this, 0. This added to this, 8. This added to this, 9. This added to this, 1. This added to this, 0. And this added to this, 1. Make sense? Then I need to get, at this point, I can see that if I just add row 2 to row 3, yes, I'm going to get a row of zeros. Yes, so I get, if I do this plus this 0, this plus this 0, this one plus this 0, at this point I can stop. I have a row of zeros, that means I will never have a leading one in that row. If I don't have a leading one in that row, how can I get I? So sometimes if the matrix is not invertible, this is how this fact will be manifested. Are we good? Example 6. Using A and B in the previous two examples, what can you say about the homogeneous linear system AX equals 0 and the homogeneous linear system BX equals 0? So this is A, and we were able to find the inverse of A. So A is invertible. If A is invertible, according to those four statements, this system has the trivial solution only. There's only one solution for this system, and that would be the origin. X can only be 0, 0, 0. What can I tell about this system? We learned that B is not invertible. We learned that B does not have an inverse. So if B does not have an inverse, this system does not have the trivial solution only. It means that it has, if you remember, there are only two possibilities for a homogeneous linear system. Generally, if you have a system AX equal B, yes, there are three possibilities. Either no solution, unique, or infinitely many. But a homogeneous linear system is different. If you have a homogeneous linear system, there are only two possibilities. Either unique, in this case that would be trivial, or infinitely many. Because a homogeneous linear system cannot be inconsistent. A homogeneous linear system is always consistent because the trivial solution is always there. Yes, it's clear that if I replace x by 0, I would get a times 0, and any matrix times 0 is 0. So for a homogeneous linear system, the no solution possibility is out. A homogeneous linear system either has unique solution, the trivial solution, or infinitely many. So for this homogeneous linear system, since A is invertible, it has this trivial solution only according to the theorem. And since B is not invertible, then this system cannot have the trivial solution only. So what's the other possibility? Infinitely many solutions. So this is what I explained here. Since A is invertible, then this system has the trivial solution only. And since B is singular, that is, if B is not invertible, then this system has infinitely many solutions. Are we good? Okay, so before I do the last example, I want you to practice the inversion algorithm. So for that reason, I want you to go to the homework set, exercise set 1.5, and do a problem with inversion algorithm. So I just want to find a matrix where I ask you to find it. Yeah, that's good. So do number 14. You're given, oh, this is a special matrix. Let's do, yeah, this one. That's better. So everybody work on number 15. Just use the inversion algorithm, and then I will also do it on the board, but I want you to try it first. So from linear algebra 1.5, access problem 15, everybody work on that. I want you to practice the inversion algorithm. Okay, so I'm gonna do it for you on the board now. First, you have to write the matrix like this: 6 minus 5, 0, minus 4, 6, 5. So next to that, you put the identity matrix. In order to transform the left side towards I need to first do 1/3 of row 1. That will give me 1, 0, 0, 1/3, 0, 0, 6 minus 5, 0, 0, 1, 0, minus 4, 6, 5, 0, 0, 1. Next, I will have to do row 2 minus 6 row 1 and row 3 plus 4 row 1. So that means the first row does not change. Negative 6 times this added to this, 0. Negative 6 times this added to this, no change. No change here. Negative 6 times this is negative 2 added to this, negative 2. And these two do not change. 4 times this to this, 0, 6, 5, no change there. 4 times this is 4 over 3. So 4 over 3. And then the other two do not change. Next step is to get a 1 here. And for that, I will have to do negative 1 over 5 times row 2. So I get 1, 0, 0, 1 over 3, 0, 0, 0, 1, 0, 2 over 5, negative 1 over 5, 0, 0, 6, 5, 4 over 3, 0, 1. Okay. Next, I need to get a 0 here. And for that, I will have to do 1/6 of, I need to do row 3 minus 6 times row 2. That means the first row does not change. 1, 0, 0, 1/3, 0, 0. The second row also does not change. 2 over 5, negative 1 over 5, 0, 0. Negative 6 times this added to this, 0. Negative 6 times this added to this, 5. Negative 6 times this is negative 12 over 5. So let me just use my calculator for that. So negative 6 times this, negative 12 over 5. Negative 12 over 5 plus 4 over 3. That is negative 16 over 15. And negative 6 times this is just 6 over 5. Added to 0 is 6 over 5. And this one does not change. And the last thing I have to do is to do row 3 times 1 over 5. And if I do so, I'm going to get I on this side. On the other side, I will get 1 over 3, 0, 0, 2 over 5, negative 1 over 5, 0. And then 5 times 15, that's 75. So I get negative 16 over 75. 6 over 25, and finally I get 1 over 5. Okay, so let me just try this. 1 over 3, 0, 0, 2 over 5, negative 1 over 5, 0, negative 16 over 75, 6 over 25, and finally 1 over 5. So that's the way to go. Is it clear for everybody?
Yes.
Okay, great. I just checked the progress of the students. Only a couple of you got the right answer. So I just want to make sure that you learn this inversion algorithm just right now. So I want you to, and these are your homework anyway. So I want you to spend 5 minutes, find the inverse of this matrix here. So number 16, also do that one. So 5 minutes for this. Okay, everybody, we got a better result with this one, number 16. So let me just, in the time remaining, finish the section by doing example 7. Example 7 says we have this matrix 1, 3, 2, 4, which we know is invertible, because when you look at the determinant of this matrix, let's call that A, it's AD minus BC. It's going to be 4 minus 6. It's going to be minus 2, which is not 0. Yeah, so we know that this matrix is invertible. And we also have a formula for the inverse of a 2 by 2 matrix, so we don't even need the inversion algorithm. But the question is, write this as a product of elementary matrices, and we know this is possible because it's in the theorem over here. We know that if A is invertible, part A, then D, A is expressible as a product of elementary matrices. So we want to do that. So if you remember, we said that if A is invertible, then there is a sequence of elementary row operations that will transform A to I. And that sequence of row operations, that would be actually A inverse. Yes. So A inverse is EK, E2, E1. And now if I find the inverse on both sides, that is, if I put a bracket inside the left side and invert that, and put a bracket inside the right side and invert that, I'm going to get A is equal E1 inverse, E2 inverse, all the way to EK inverse. So using this, I can find a series of elementary matrices so that A is the product of those elementary matrices. I can express A as a product of elementary matrices because each one of these is actually an elementary matrix. So how do I do that? I need to keep track of the elementary matrices that I perform on A. So first I need to do E1 on A, then E2 on A, all the way. I need to keep track of them and then find E1 inverse, then E2 inverse, then E3 inverse, all the way to EK inverse, and then I can multiply them in this order. That would be A expressed in terms of a product of elementary matrices. So let's try to do this one. I want to write this matrix A, 1, 3, 2, 4 as a product of elementary matrices. So first of all, I need to transform that into I. So I have 1, 3, 2, 4. I'm just going to erase this and use the whole board. First, I need to transform that into I. So the first thing I need to do is this row operation. I need a 0 here. So row 2 minus 2 row 1, right? 1, 3, negative 2 times this added to this 0, negative 2 times this, negative 6 added to this negative 2. So that's the first row operation. Yes. That would be like E1. So E1 would be like this. I have to perform the same row operation on I to get E1. If I do that, I get 0, 1, 0, negative 2, 1. Is that clear? Then I need to perform a row operation on this one. And that row operation would be multiplying this by negative 1 over 2 so that I have a 1 here. So negative 1 over 2, row 2. 1, 3, 0, 1. And the corresponding elementary matrix would be 1, 0, 0, negative 1 over 2. Next, I would need to do row 1 minus 3 row 2. And this will give me I. Yes, negative 3 times this added to this gives me I. So I got I. And row and E3, which corresponds to this row operation, is going to be 1, negative 3, 0, 1. I just added negative 3 times row 2 to row 1. I got this. Now, according to this, the algebra that I just showed you, and it is also written here, A is E1 inverse times E2 inverse times E3 inverse. Yes, so what would be E1 inverse? I need to think about the canceling row operation and perform that row operation on I to get E1 inverse. The canceling row operation for adding negative 2 times row 1 to row 2 is adding 2 times row 1 to row 2. So it's going to be 1, 0, 2, 1. The canceling row operation for multiplying the second row by negative 1 over 2 would be multiplying the second row by negative 2. So we're going to get 0, 1, 0, 0, minus 2. Is that clear? The canceling row operation for negative 1 over 2 row 2 would be negative 2 times row 2, which will produce E2 inverse. And the canceling row operation for adding negative 3 times row 2 to row 1 would be adding 3 times row 2 to row 1, which will give me 1, 3, 0, 1. So that would be A expressed as a product of elementary matrices. Notice that I actually did not need E1, E2, and E3. I would only need to keep track of the row operations. Because if I keep track of the row operations that I perform to reduce A to I, then from these row operations, I can get E1 inverse times E2 inverse times E3 inverse. I just need to think about the canceling row operations and perform them on I. Is that clear? Any questions?